Okay, so moving right along in chapter 17 on lipids. Now we've talked a fair deal about the fatty acid chains and the different triacylglycerols, and we ended our last lecture talking about the content of saturated, monounsaturated, and polyunsaturated residues there, and how they tend to stack up, with the animal fats tending to have more of the saturated and the plant sources tend to having more of the unsaturated, although that coconut oil was really high saturated content, and it's one of our few oils that's actually a fat, a solid at room temperature and pressure. In this lecture, we're going to look at the chemical properties of those triacylglycerols. We'll look at some of the processing and various reactivity of those triacylglycerols, what they do in the body, and what we as chemists can do to them in the lab. Now, because of the fact that the triacylglycerols tend to involve an ester linkage of either alkane or alkene type residues, we tend to see the chemical reactivity of the triacylglycerols similar to those of the alkenes, since the alkanes don't do too much chemically, and the esters. So in hydrogenation, for instance, double bonds in unsaturated fatty acids can react with hydrogen in the presence of a nickel or platinum catalyst. So this is done in the lab, not in the body. So we have the fatty acid residue that has a double bond, whether it's a monounsaturated or polyunsaturated. Typically it's the polyunsaturated that get partially hydrogenated in the lab in the presence of hydrogen on a nickel catalyst, and we can saturate those former double bonds into single bonds. In hydrolysis, the ester bonds are split by water in the presence of an acid, a base, or an enzyme, and so that's another reaction that triacylglycerols can undergo because of their ester bonds. So here we see hydrogenation of glyceryl triolate. So in this hydrogenation reaction, hydrogen adds across a double bond to form carbon-carbon single bonds, and we turn that glyceryl triolate, something that we'd likely find in an oil rather, like olive oil, into our typical fat, the glyceryl tristearate, which would be a tristearin, a saturated, fully saturated fat from an unsaturated oil. Okay, so the hydrogenation of oils converts these double bonds to single bonds. In the previous example, we fully converted it. That's not typically the case. Usually it's a partial hydrogenation. So it adds hydrogen to carbon atoms of double bonds, but not necessarily all the double bonds. As a result, it increases the melting point, and it can produce solids from oils. So things like margarine and shortening can be made from these vegetable oil liquids. So they're soft solids, and it was a big improvement because I think it was in France at wartime, Napoleon wanted something for his soldiers to spread on their bread, and you couldn't have butter. It didn't travel well in the field, and so the French chemists worked on and finally generated this margarine by hydrogenating these plant vegetable oils. Of course, the problem with hydrogenation is it's partial, so you don't saturate every residue, and you tend to end up with some trans fats, trans double bonds now, and shortening. Crisco there is our picture, but shortening is the one thing that you really can't get rid of the trans fat. So if you enjoy your Crisco for cooking, you're consuming trans fats. It's the one thing that when they started requiring the label to indicate the trans fat content, Crisco just came clean with it. They didn't try to get rid of it because you really can't for shortening. They just indicate it, and people who use the shortening just should understand that they're consuming trans fats. There seems to be an increased link with heart disease and trans fat consumption, but again, if it's worth it, if you really enjoy your shortening and there's no alternative, then I guess it's worth the risk. All right, so let's pause for a learning check before we move forward. So which of the following products is obtained from the complete hydrogenation of glyceryl triolate? Do you get A, glycerol and 3 oleic acids? Do you get B, glyceryl tristearate? Or do you get C, glycerol and 3 stearic acid residues? So go ahead and answer this question. Stop the video if you must, and once you're ready to check your work, start it back up. Good luck. Okay, and hopefully you selected choice B, glyceryl tristearate. Of course, in a hydrogenation, we're not breaking the ester bond, so we're not going to free these fatty acid residues. We're just going to saturate them. So the oleic acid residues are now going to be stearic acid residues, but they're going to remain in the ester linkage as glyceryl tristearate, not as a glycerol and 3 stearic acid residues. Okay, so hopefully that's what you picked, and if you didn't, hopefully you understand now why that would be the correct answer. If you're stuck, you're just having trouble getting this concept, you could take a look at it, try some additional practice problems, and certainly reach out to me if necessary. Okay, so let's talk about trying to trick the body. So olestra is a fat substitute. It's used in foods as an artificial fat. I don't know how popular it is anymore. It was a big deal in the late 90s, early 2000s when it first came on the market. And then I think many of the foods they tried it in tended to result in some abdominal discomfort for the consumers because you can't digest it. It's composed of 6 to 8 long chain fatty acids attached by ester linkages to a sucrose, not a glycerol molecule. So sucrose, of course, is that disaccharide with a fructose joined to a glucose. And you can see that that doesn't look like anything we've talked about so far. The body doesn't have the enzymes needed to break it down. We can't do anything with it. Some bacteria can do some actions on it, and they tend to be able to thrive. And so it just it's not broken down in the intestinal tract ordinarily by humans. Whether the bacteria are able to break it down or whether they're just able to cause some intestinal havoc, I'm not sure. I don't know what the research says, but I know a lot of foods that tried it, the Olestra was just not well received by the public. Lots of stomach aches and just not an enjoyable experience. Maybe they've cut down on the amounts, or maybe they've removed it from most foods, but it was a really big deal when it first came out, and I just haven't heard so much about it these days. All right, as we've mentioned before, cis and trans fatty acids exist. The unsaturated fatty acids tend to be cis in nature, almost exclusively cis in nature, with the bulky groups on the same side of that carbon-carbon double bond. The trans form tends to be unnatural. It tends to be the result of human hydrogenation reactions out of the body in the lab using the nickel or palladium or platinum catalysts that we've mentioned before, and those are preferred products of that sort of external hydrogenation, whereas cis fatty acids that are made in nature are much bulkier and seem to be much better tolerated by the human body. So as we've already discussed, the trans fatty acids get formed when you're doing an incomplete hydrogenation, a partial hydrogenation of a substance containing multiple double bonds, where you convert some of those double bonds into single bonds, but other double bonds, cis double bonds, get converted into trans double bonds. So in the body, these behave like saturated fatty acids. They're estimated to make up about 2 to 4% of the total calories people consume. And again, the American Heart Association recommends the use of soft margin, which is only slightly hydrogenated, therefore fewer trans fatty acids than the other margarines, which are more highly hydrogenated and tend to have greater amounts of these trans double bonds. As I mentioned a couple slides ago, the margarines you can avoid, probably just a little bit of butter is the safer option these days, but shortenings tend to have lots of trans fatty acids. There's just no other way to do it. And then if you're consuming a lot of that, you're going to be talking about more than that 2 to 4% of the total calories that most of us would consume with minimal trans fats by trying to avoid things that would have trans fats present. Now, in the vegetable oils themselves, as we said, the unsaturated fats usually contain cis double bonds. during that hydrogenation process in the lab, some of those cis double bonds get converted into trans double bonds because trans double bonds are more thermodynamically stable, although, again, nature probably has a reason for what it does, and certainly we've evolved to go with nature's cis double bonds, so when we cause that change to the fatty acid structure, there tends to be consequences, and one of those consequences based on long-term research seems to be a higher incidence of heart disease with large consumption of trans fatty acids. Okay, so we see here a cis oleic acid being hydrogenated on a nickel catalyst. So the successful hydrogenation should give rise to a saturated product, a stearic acid from the oleic acid. Unfortunately, some of the time, the nickel catalyst doesn't allow for hydrogenation to occur, but instead catalyzes the isomerization of the cis oleic acid into the trans oleic acid. So the undesirable product that just will occur in some amount in addition to the desired saturated product. So now that manufacturers have to disclose these if they reach a certain amount. Again, there's probably some amount, anything that says partially hydrogenated on the label is going to involve some amount of the trans fatty acids. If it's a small enough amount, they don't have to disclose it and they can claim zero trans fat. But once it gets to a half a gram or more, then you're going to see it on the label. And if you're really concerned about that, then you should avoid those products. There's nowadays a lot of alternatives that have essentially no or very small amounts of the trans fatty acid residues. So it's not so difficult to avoid those trans fats as it was before the manufacturers had to disclose them. Okay, so let's pause here for another learning check. This time you're asked to identify each statement as true or false. And again, we'll say largely true or largely false. So A, there are more unsaturated fats in vegetable oils. Is that usually true or usually false? So that sort of thing. Okay, so go ahead and respond to that learning check for those 4 items. Stop the video while you make your determination and start us back up when you're ready to check your work. Good luck. Okay, so hopefully you arrived at these answers. So for A, hopefully you said it's true. There are more unsaturated fats in vegetable oils. Usually, again, coconut oil did give rise to that very high saturated fat content, and that was our one exception, but as a rule of thumb, that statement is true. For B, vegetable oils have higher melting points than fats. Well, no, that's false. Our vegetable oils tend to be oils, liquids at room temperature and pressure, aside from coconut oil and palm oil, whereas the animal fats tend to have higher melting points and be solids at room temperature and pressure. For C, hydrogenation of oils converts some cis double bonds to trans double bonds. That's true. And finally, D, animal fats have more saturated fats as a rule of thumb than plant sources, again, with coconut and palm being exceptions to that. So hopefully you got those. If you were caught by those exceptions and you didn't really want to call those things true, I feel for you. I'm with you there. I'm a scientist. I like to be very exact about things, and here we're being a little less exact than usual. So as long as you understand why we made these determinations, even if you're not entirely comfortable with the first and the last one, hopefully you're having a good handle on all this, and I think you'll be in good shape come test time. If that's not the case, then certainly reach out for some guidance. Now, the other reaction, we looked at hydrogenation as a result of those unsaturated fatty acid residues. The other key reaction we'll talk about here for the triacylglycerols is hydrolysis. So in acid or enzyme hydrolysis, water adds to the ester bonds. The triacylglycerols hydrolyze, forming the glycerol and the 3 fatty acids that they're made up from. And then a strong acid such as HCl or H2SO4, not very bio-friendly, right? But we could do that in the lab. Or an enzyme catalyst that's much more bio-friendly is required to do that. And this is how in our human bodies we can use enzymes to break down the triglycerides into glycerol and the 3 fatty acid residues. So we see here the glycerol tripalmitate or tripalmitin plus 3 waters is in either the presence of a strong acid like HCl or sulfuric acid, or the lipase that would do this all bio-friendly can reform the glycerol and the 3 fatty acid residues. So this is the reverse of the process we saw before, the esterification to make the triacylglycerol. Now we're taking that triacylglycerol and water and reforming glycerol and the 3 fatty acids. If, on the other hand, this hydrolysis is done in basic conditions, it's known as saponification or base hydrolysis. And in this case, the triacylglycerol reacts with heat and a strong base. And because you're in a base, the triacylglycerol splits into glycerol. That's still normal, but you get the salts of the fatty acids, right? They're acids, so they react with the base to form the salts. And so a solid soap that can be molded into the desired shape is usually produced with NaOH or KOH if you want a softer soap. So the solid soaps, you go with the sodium hydroxide. The softer liquid soaps, you would go with potassium hydroxide. And also, if you look at the fatty acid residues themselves, if you get polyunsaturated oils, you'll produce softer soaps than if you get the monounsaturated or saturated fatty acid residues. So things like sodium stearate would give a nice solid soap, whereas potassium oleate would give a softer soap. Okay, and here we see that the general scheme is a fat or an oil, a triacylglycerol, which would either be a fat from animal sources or an oil from plant sources, plus a strong base gives rise to glycerol, plus the salts of those fatty acids, the soap. And so we see here glycerol tripalmitate. That's going to be a nice saturated fat, so that's going to give us, when we combine it with 3 NaOH moles, we get the glycerol and we get 3 sodium palmitate residues, which will give us a nice hard solid soap. All right, so table 17.3 here, we see the summary of reactions we've talked about. So we talked about esterification, which was taking the carboxylic acids, those fatty acids, and the glycerol in the case of chapter 17 content, or generically carboxylic acid and alcohol in the presence of an acid catalyst and heat, or biocatalysts, enzymes. We could get the ester and the water, and so we see that with the lipid reaction on the right-hand column, the 3 fatty acids plus glycerol in the presence of an enzyme to make our triacylglycerol, our fat, plus water or oil, depending on what we end up with. In the case of hydrogenation, we had an alkene plus hydrogen. In a case of a platinum or palladium or nickel catalyst, gave us an alkane. When we look at the right-hand column now, in a lipid reaction, we tend to see this with an unsaturated fat, so at least 1 double bond, plus hydrogen on a platinum catalyst will give us a saturated fat with single bonds, plus some amount of that trans unsaturated fatty acid product. Finally, for hydrolysis of the ester, we can either do that with the ester in the water in the presence of an acid and heat, when we were talking back in our chapter on esters, to make the carboxylic acid and alcohol, or in the case of chapter 17 here with triacylglycerols, fats or oils, plus water, 3 moles of water for every triacylglycerol. In the presence of a lipase enzyme, we can regenerate the 3 fatty acids plus glycerol. And finally, if we did that same reaction in the presence of a strong base instead of an acid catalyst or an enzyme catalyst, we would get the ester plus the sodium hydroxide or potassium hydroxide to give a sodium salt of the carboxylic acid plus an alcohol in general organic chemistry. But in a lipid biological sense, you'd see that triacylglycerol, the fat or oil, plus 3 sodium hydroxide would give rise to 3 sodium salts of fatty acids, the soap, plus the glycerol. If we wanted a softer soap, we'd use potassium hydroxide and higher unsaturated fatty acid content. So there we go, a nice summary of those reactions for both the generic organic chemistry cases that we've seen previously, and now the specific lipid reactions. So before we leave our lecture on chemical properties of triacylglycerols, let's pause for a couple more learning checks. So first, we're going to address the learning check that asks what products are obtained from the complete hydrolysis of glyceryl trioleate. Do we get A, glycerol and 3 oleic acids? Do we get B, glyceryl tristearate? Or do we get C, glycerol and 3 stearic acid residues? Pause the video here while you make your determination and start back up when you're ready to check your work. Good luck. Okay, so this time we're looking at hydrolysis. So we're just taking that ester bond and breaking it down for the 3 ester linkages we have in our glyceryl trioleate. So we're not hydrogenating, so we're not going to end up with the stearic acid residues. There's still going to be oleic acid residues, but there's going to be 3 of them along with the glycerol. So hopefully you selected choice A and you understand why you did so. If not, if you're struggling, let's do another learning check and hopefully things will improve. Okay, so for our last learning check in this lecture, we're asked to draw the condensed structural formula, or of course, you know, I'd prefer the skeletal structure of the product of the following reaction. So we have here a reaction where we're taking that triacylglycerol, we're adding 3 moles of hydrogen on a nickel catalyst, and your job is to draw the product. So stop the video here while you draw that final product or products, and start it back up when you're ready to check your work. Good luck. Okay, so there's our major product, right? We've saturated all those double bonds to single bonds. It's still a triacylglycerol, but we've added those hydrogens across each of those double bonds of the 3 fatty acid residues. Of course, we're going to get some trans fatty acid results. We're going to have some unsaturated residues that don't add hydrogen. Instead, they isomerize from the cis to the trans isomer, but that's a minority product. Here we're looking at the majority product, and so this is what I would expect. If you had the others, if you had some of those converted to trans from cis, great, that's wonderful, but that's probably a higher level than we're really looking at for this course. So hopefully things are going well. We're well into chapter 17 now. Things should be making sense. If they're not, and if you've checked some other end of chapter problems or the homework sets and you're still struggling, then please do reach out to me and we'll see what we can do to get you where you need to be. Otherwise, if everything's going swimmingly, as I hope it is, we'll see you in the next section of chapter 17.